So here comes the C-star algebra of the day, and my choice this time is a very canonical one. It's the so-called UHF algebra, which plays a very important role in the history of C-star algebras. So UHF stands for uniformly hyperfinite. I'm not sure this helps anybody, but this is where this notation comes from. So usually this C-star algebra is defined in a different way, but it would take me a bit too far away from things that we have talked about. So I'm going to give you sort of a homemade definition of it, which is not original, but it's just not the easiest way if you have the right tools. But for the tools that we have here, this is probably the best way of doing it. So I want to show you this particular C-star algebra as a subset of B of H, and I'm choosing a particular Hilbert space. Of course, all separable Hilbert spaces are isomorphic as Hilbert spaces, so that doesn't really matter which one we take. But for notational reasons, I want to think of this as little L2 of n0. So we think of the elements as infinite vectors or sequences that are L2 summable. And then the C-star algebra I'm going to show you will lie inside B of H. So all the operations that we need to create a C-star algebra, I inherit those from B of H. And so what I'm going to do is I will define AN to be the set, let's just say, of T's in B of H, having satisfying some conditions that I will call just dagger, and let me write them up. So T, E, I, comma, E, J will be the same as T, E, I plus 2 to the n, comma, T, E, comma, E, J plus 2 to the n. This is for all I and j in n0. And if I is strictly less than 2 to the n and weakly less than, and j is weakly bigger than this, then I require that T, E, I, E, J is 0. And similarly, if the same holds, then T, oh, sorry, I'll write it this way, T, E, I, E, J is 0. Now I've written the same twice, but I'm going to change the sides here. So it will be for the J's here, the I's here. Okay, so this perhaps doesn't make a lot of sense. So let me try to show you what this looks like in a matrix picture. So, of course, I'm talking about a bounded operator on an infinite dimensional Hilbert space, so it doesn't make sense to talk about a matrix. But of course, we can always, when we have an operator like this, we can create a matrix where we just compute these inner products TEI up against TJ. And this will be the same as, I mean, this is precisely what you would do if you had a finite dimensional Hilbert space, and then you would write up the matrix this way, because I have an orthonormal basis, right? So really what is happening is that I'm taking TEI and I'm expanding it in the basis EJ, and to get the coefficients for this, I just need to take inner products. And so if we start, so I have this definition for all n, and by the way, this is, maybe I should call this dagger n, right? So maybe we should start by looking at n equals 1 and see what this actually says. And the first thing that is going on is that suppose that we start by saying that the entry up here, which is TE0E0, I will call this A00. Then I have A01 and A10 and A11. And then you can see that the whole matrix is going to be determined by these values here, because the first rule that I have, the one I will highlight it in blue. And so this rule here, this says that if I take any entry, for instance this one here, right, this is some entry, that's going to be the same if I take the first value and increase it by 2, and the second value and increase it by 2. So it would be like, maybe if I sort of put little dots here, then what I'm saying is that whatever is written at these two big blue dots will have to be the same. And so what's happening here is that then clearly this means that if I've told you, for instance, what we have in the two first rows of this matrix, right? So if we just take these two rows here, then by the repetition rule, I have told you what will happen everywhere else. And this I can easily do from the other two axioms, because the other two axioms says that if I'm in a situation where I and j are separated by by 2 to the n, so I mean this means that I is strictly less than 2 and j is bigger than or equal to 2, then these inner products must be 0. So really what this means is that whenever we have a situation where we're looking at an element here, which is the 0, 2 element, right? So this corresponds to having I equals 0 and j equals 2, then we have to get a 0, right? And also we have to get a 0 here, we have to get a 0 here, we have to get a 0 here, and the same down here, right? So I also need to know what happens here and here in order to get all the information about what the matrix looks like. Right, so I have 0, 0, zeros, and then if I move this a little bit out of the way, then you can see that now I have a repetition of A00, A01, A10, A11, and so on. Right, so this matrix has a lot of zeros. That's what dagger 1 means. And the only thing that is sort of going on is that you have a 2 by 2 matrix, which is sort of repeated down the diagonal. So the way you should think about this is that A1, and this can be formalized if you want, is isometrically isomorphic to the 2 by 2 matrices of C. But then you can sort of say, what happens when we do this again with n equals 2? So maybe I'll just draw this here again. If I have n equals 2, then the situation is that I will have this time 16 numbers, so maybe I will not write them all. A10, A11, A12, A13, okay, I'll write them all. A21, A22, A23, A30, A31, A32, A33, and then I will get zeros after that, and I will get this repeated again down here, because this time the repetition rule says that, you know, if I have, for instance, a number here, that's going to be the same if I go 4 across and 4 down. So this would be like this. So those have to be the same, right? So just like before, since I know what's going to happen in the 4 first rows and the 4 first columns, I know what's going to happen in the rest of the matrix. So if you just see what this means, this is precisely like saying that A2 is the same as M4, and A3 is the same as M8, and so on. So, I mean, so you may wonder why I'm doing it this way. It's sort of just a complicated way of finding a C-star algebra which lives in an infinite dimensional Hilbert space, but it's finite dimensional. But the point of doing this is of course, that I mean, these are the same up to isomorphism, these are the same up to isomorphism, these are the same up to isomorphism. But the point is that it's clear that A1 sits inside A2, and A2 sits inside A3, and A4 sits inside A4. A3 sits inside A4, and so on. So really, you know, if you allow me to do sort of a less formal picture, right? So, I mean, the first time I get something with values that look like this, right? So these are the 2 by 2 matrices, and they live inside my infinite dimensional Hilbert space in this particular way. And then the next time, use another color, then I get the 4 by 4 matrices. They live like this, and I repeat them like this. And the next time again, I get, you know, the 8 by 8 matrices, and they live, you know, like this, and so on. So you can perhaps see that I'm nesting these. The whole point of this construction is that I'm putting the 2 by 2 matrices inside the 4 by 4 matrices, inside the 8 by 8 matrices, and so on in a controlled way. So the definition of the UHF algebra is just, usually it's called M to infinity, is just that I will take the union of all these ANs and then take the closure inside B of H. Right, so my A1, A2, and A3 and so on are nested. So when I take the union of them, I will get something which has all the operations well defined. Because if I want to convince you, for instance, that the union of all these ANs with n equal bigger than or equal to 1, if I want to convince you that, for instance, I can take two elements and I can add them up, right? So it's two elements that come from this union. So x comes from AN1 and y comes from AN2, and I want to convince you that it makes sense to, for instance, take their sum, right? But then the point is that one of these two indices, n1 or n2, is the biggest one. So let's say perhaps n2 is the biggest one, right? So then a and 1 also, x lies in a and 1, but that's inside a and 2. So I can think of x as coming from a and 2, and y already came from a and 2, so it makes sense to add them. And I can multiply, I can take stars, whatever. So I will get what's usually called a pre-C-star algebra, satisfies all the axioms, but it's not complete, right? So in order to make it complete, we just need to close it off inside B of H, which we already know is complete. So this is a UHF algebra, and there's some properties, and I won't be able to prove this, but perhaps you can get the idea. So first of all, and these properties are different from the properties of B of H. So I'm claiming, for instance, that M to infinity is separable. So there is a dense sequence in it. That's not true for B of H. It's an inseparable C-star algebra. It's too big to have a dense sequence. But of course, since all the matrix algebras have a dense sequence, then you can sort of use that and take it to the limit and get a separable sequence in M to infinity. So that's fairly easy. Actually, M to infinity is also simple, meaning that it has no non-trivial two-sided closed ideals. This again is different from B of H, where we know we have the compact operators that defines an ideal. But just because the matrix algebras are simple, there's no ideals in there, essentially, because if you have a non-zero element in a matrix algebra, you can use that to generate everything just by multiplying on with matrix units. So that's fairly easy. So this is something that is false for B of H, but it's true for this subalgebra. Another important observation is that M to infinity contains no non-unitary isometries. So we've seen at the beginning of the course that it's easy to find these sort of shift type isometries that are not unitaries in an infinite dimensional Hilbert space. So this is always the case in B of H. But here, just because there are no non-unitary isometries in a matrix algebra, just that this is, the rank nullity theorem tells you that if you have a matrix which is say injective, then it also has to be surjective. You can take that to the limit and show that the UHF algebra also has this property. This is often called a finite C-star algebra. And finally, also, of course, this sets it apart. So I said that this sets it apart from B of H. What I meant was that it sets it apart from B of H with H infinite dimensional. But of course, it's also not the same as just matrix algebras because it's infinite dimensional, because I've sort of made it by subalgebras that get bigger and bigger. So this particular C-star algebra is extremely important, in particular because it shows some behavior that in the beginning of the C-star algebra theory was thought to be impossible, actually. So people thought that any C-star algebra would have some properties that this particular C-star algebra does not have. And so this started out when this was studied in the late 50s and early 60s. James Glim was a big mathematician working on this. This sort of showed that the universe of C-star algebras is much richer than it was believed to be. So back then, this was considered a very sort of pathological type of C-star algebra. But then, I guess what often happens in mathematics is that the pathology of one generation becomes the key examples for the next generation, and this is today is considered a very nice C-star algebra. We know a lot about it. But this sort of shows you that you can get behavior that is a lot like the finite dimensional case, even though you have an infinite dimensional setup. So let me stop here.